Hello, hello, hello. Today we're covering part 2 of Change in Tandem 1.1, which is, I'm sorry, chapter 1.1 in unit 1. Water is poured into an empty vase at a constant rate. A graph not shown, the graph is not shown, it models the depth of the water in the vase over time. The graph can be described as follows. The graph is always increasing. The first portion of the graph is clearly concave up. Now, a graph that is increasing and concave up looks like this. Now, a graph that's increasing and concave down looks like this. However, we're dealing with the left function, right? The left graph. So it's increasing but concave up. And the next portion of the graph has a fairly steady and steep increase. So it looks like this. Now, which of the following phases is appropriate for the context described by the graph? Now, we're trying to translate this graph into one of the options. Well, this basically tells us that it takes time for water to build up, and then as it increases, it then increases at a steady rate. So this means that at the top, it's going to be, I would say, pretty straight. Now, it is thick at the bottom because it takes time for it to build up water. As you can tell, it takes some time for it to build up, which basically means it is, in fact, option B. Now, why isn't it D or C, right? Well, with C, we have 3 parts to it. Like, this is one part, this is the second, and this is the third. And we only got 2 parts in this graph, 1 and 2, as you can tell. 1, and this is the second. Now, why isn't it D? Well, same story. We got 1 part, we got this part, then we have this part. Well, why isn't it A? Because we also got 1, 2, and 3 parts. And B perfectly translates the given graph into a vase. Okay, moving on. Question number, if this was 9, okay, we got 10. The graph shows a swimming pool filled with water. A pump is used to remove water from the pool until the pool is empty. When the pump is running, the rate at which the volume of water in the pool decreases is constant. So the rate at which the volume of water in the pool decreases is constant, which basically means we're dealing with a straight line, right? During the first 2 hours, the pump works slower than usual due to a broken piece. So during the first 2 hours, the pump works slower than usual due to a broken piece, which means we're going to have to be looking at the first 2 hours where this rate is slower than the remaining parts of this graph. Okay. Then the pump stops working. Okay. The broken piece is replaced and the pump works at its usual rate until the pool is completely empty out of water. The entire process of emptying the pool takes 6 hours. So after 6 hours, the pool should be empty. Well, this is at mark 10. This is at mark 6. This is at mark 6. And this is at mark 6. Okay, we're good so far. So A is out. We have what is left. What is left is B, C, and D. And they also mention that, okay, well, they mentioned that during the first 2 hours, this is slower than this, right? Then it gets fixed. So the second part should be faster, but in option C, that's definitely not the case. Now we need to decide on whether it's B or D, right? Now, did they mention... Oh, wait, my bad. Okay, yeah. Yeah, well, why isn't it D? Because it was working fine for the first 2 hours, then it broke, right? At the 2 hour mark, they started fixing the pump. As you can tell, at the 2 hour mark, let's go back to the context. During the first 2 hours, the pump works slower than usual due to a broken piece. Then it stops working. So during the first 2 hours, it was working fine, then it stopped working. Then it got fixed, then it worked. It's not A because it took them 10 hours to empty this pool. It is definitely B because at 2 hours it stopped, then they fixed it, faster rate, at 6 hours we're done, which is the answer. It's not C because they mentioned it was working slower than usual. Well, these two lines have the same exact rate, and it is not D because it breaks at the mark at the second hour, and that's not the case. So it is definitely option B. That's it. Moving on. The figure shows a sphere that can expand. As it expands, the volume inside the sphere and the radius of the sphere both increase. In particular, the radius increases at a decreasing rate with respect to the volume. So if it's increasing at a decreasing rate, and this is what it looks like. Actually, let me write them down for you. So increasing, and let's say with an increasing rate, this is what it looks like. Concave up. How do I know? Not because of the first word, but because of the second. Increasing rate means concave up. All good? Now, what if it's decreasing with an increasing rate? Well, it is still concave up, and it looks like this. Okay? If you want to memorize these two, go ahead. So whenever you see the word increasing rate, it's going to be concave up. What else do we have? Well, okay. Let's erase just this part. Now let's say it's increasing with an increasing with a what? Sorry. Yeah, let's go with decreasing this time. Okay. Increasing with a decreasing rate. So increasing with an decreasing rate. So if it's increasing with a decreasing rate, it's going to look like this. Concave now. because it mentions decreasing rate. Now, what if it's decreasing with a decreasing rate? It simply looks like this. It's concave now. So whenever you see the word decreasing rate, know for a fact that it is concave now. Now you can memorize this as well. What do we have in this case? It's increasing at a decreasing rate. So this is simply the graph. Increases at a decreasing rate. This is what we're searching for. Let's have a look. We're searching for this. That's just option B. Increasing at a decreasing rate. Concave down. It's that simple. Okay. Let us move on to number 12. At time equal t equals 0, water begins pouring into an empty container at a constant rate. The water pours into the container until it is full. This situation is modeled by the given graph, where time in seconds is the independent variable and the depth of water in the container in centimeters is the dependent variable. For which of the following containers would the graph be appropriate? Well, it does. Okay, well, it's quite slim through the middle, right? You could say it's quite constant. That's exactly what we're searching for. You could tell that it's quite constant through the middle. And the top and the bottom, we have a variation, right? You got some time for it to build up. In this case, it's definitely not A, because or else this would have been just like a constant straight line. But since we have a constant straight line through the middle, and okay, here we go, some variations going on, then it is definitely B, not C, because through the middle, it was actually slim. It was faster, right? And, well, D is definitely not the answer, because it takes more time at the bottom, as you can tell, than through the middle. It's taking some time at the bottom. So it's the opposite. D is the opposite of B. And D is out. Same with C. The answer is definitely B. Well, these questions are quite annoying, I get you. But they're good practice. They don't really show up. I don't take my word for this, but they don't show up much on the AP. But it is good to understand how concavity works and how you can translate graphs into real life situations, I would say. Are you ever going to use this in your life? I'm pretty sure no. But anyways. Moving on to this one. For T between 0 and 16, the rate at which customers arrive at a restaurant on a given day is modeled by the function R, where R of T is measured in customers per hour and T is measured in hours since the restaurant is opened. Now the function R is increasing for T, which is between 0 and 4, and T between 8 and 12. It's increasing. The rate is increasing, right? They mentioned that? And R is decreasing because R represents the rate, isn't it? Yes, it does. So if they're mentioning that it's increasing, that means concave up, right? And it's decreasing for the following values. The function n models the total number of customers who have arrived at the restaurant since it opened up to time t. So function n represents the total number of customers. And what does that tell us? It simply tells us that the total means it's always increasing, right? So if at hour 1, let's say hour 1, 10 customers joined, even if at hour 2, no one joined, it's fine, the number won't decrease. Then at hour 3, let's say 5 customers joined, the total would be 15, and so on and so on. But what do they mean by a decreasing rate, increasing rate, and so on? Let me explain this. Let's say hour 1, 20 customers join. And then at hour 2, 25. And then at hour 3, 30 customers. Is the rate increasing? Yes. With every single hour, 5 more customers are joining us. But what if at hour 1, only 10 customers join? Hour 2, 5. And then at hour 3, 0. Well, it's still increasing, look. I'm sorry, the rate is decreasing. The total is still increasing, that is true, but the rate at which the number of customers is joining is decreasing. And, okay, moving on. Let's erase this. I'm not sure how I made this shape. Anyways, I believe I can erase it. There we go. Let's move on to the graph. So 0 to 4 and 8 to 12, the rate is increasing. 4 to 8, 12 to 16, the rate is decreasing. What does that mean? When I look at this interval, I'm searching for a concave up shape. I'm looking at this interval, these two, I'm looking for a concave down. So it's definitely not A or B, because the total is always increasing, as we've mentioned. So 10, 5, 15, even if this is 0, let's say it's 2, it would be 17, and so on and so on. The rate is decreasing. Let's say this is 1, it would be 18. The total number of customers joining is always increasing, but the rate at which the number of customers is joining is decreasing. Now, 0 to 4, I'm searching for a concave up. This is 0, and this is 4, it's concave up. Now, 8 to 12, it's concave up. 4 to 8, concave down. 12 to 16, concave down. Yeah, it is definitely option D, and that is it. It's that.